But once you peel back the layers, it's essentially just a very efficient way to pack a suitcase. If you're looking to master the basics or prepare for an interview, here are the must-know concepts that form the backbone of the Docker ecosystem. 1. The into the weeds, you have to understand the life cycle of a Dockerized application. Images. Think of these as a read-only snapshot or a blueprint. It contains everything your app needs to run: code, libraries, environment variables. Containers. This is the running instance of an image. If the image is the recipe, the container is the meal. Containers are isolated, meaning they don't naturally talk to each other unless you tell them to. Docker Hub ZAD registry. Your images here to store them and pull them when you're ready to deploy on a new machine. 2. Dockerfile, the automation script. A Dockerfile is a simple text document containing all the commands a user could call on the command line to assemble an image. Key instructions. From sets the base image, e.g., Ubuntu or Python. Copy moves files from your local machine into the image. Run executes commands like installing packages during the build process. CMD, the command that runs only when the container starts. 3. Persistent data, volumes, and bind mounts. This is a fancy way of saying that if a container crashes or is deleted, any data created inside it vanishes. To save your data, like a database, you use volumes, managed by Docker, the best way to persist data. Bind mounts maps a folder on your actual computer directly into the container. 4. Docker Compose, the conductor. Most modern apps aren't just one thing. They are a web frontend, a database, and a cache. Running these manually with Docker Run is a headache. Docker Compose allows you to use a link to .yml file to define and run multi-container applications with a single command. 5. Networking. By default, Docker creates a virtual bridge. Containers on the same network can talk to each other using their container names as host names, which is incredibly handy for keeping configurations clean. Network type. Use case. Bridge. The default, used for standalone containers talking to each other. Host. Removes isolation between the container and the host machine. None. Complete isolation. No outside world access. A note on images versus virtual machines, VMs. It's a common mistake to think Docker is just a lightweight VM. While they both provide isolation, VMs include a full guest operating system, whereas containers share the host's OS kernel. This is why a container starts in seconds, while a VM takes minutes. Would you like me to walk through a specific example, like creating a Dockerfile for a Python or Node.js app?
Okay. और की और पिक्चर का प्रयोग कर
To understand Docker's architecture, it relies on a decoupled design, meaning the part you interact with, the client, doesn't necessarily have to be on the same machine as the part doing the heavy lifting, the daemon. Here is the breakdown of the major players in the Docker ecosystem. 1. The three primary components. A. Docker client, Docker. The client is the primary way most users interact with Docker. When you type a command like docker run, the client sends that via a REST API. It acts as the remote control for the entire system. B. The Docker host, the daemon. The Docker daemon, Dockered, is the brain running in the background on your host operating system. It listens for API requests and manages all the heavy-duty objects, images, building and storing them, containers, starting, stopping, and monitoring them, networks and volumes, managing how data flows and stays persistent. The registry, A registry is a stateless, highly scalable server-side application that stores and lets you distribute Docker images. Public, Docker Hub is the default public registry. Private. Many companies use their own private registries like AWS ECR or Google Container Registry for security. 2. The low-level tech. Docker doesn't actually invent isolation. It leverages powerful features built directly into the Linux kernel. Feature. What it does: namespaces, provides the isolation. It ensures that a container cannot see or affect processes, files, or networks in another container. Groups, provides resource management. It limits how much RAM or CPU a specific container is allowed to use, so one app doesn't crash the whole host. Union FS allows Docker to use layers. This is why images are so small. They share common layers rather than duplicating the entire OS every time. 3. The object workflow. The architecture follows a very specific flow of data and commands. 1. The Dockerfile to create an image. 2. Pull. You download an image from a registry to your host. 3. Run. The daemon takes that image, layer on top of it, turning it into a container. Summary. The workflow equation. In architectural terms, you can think of the relationship like this. Would you like to see how these components interact in a real-world scenario, such as deploying a web server? To illustrate how these architectural components work together, let's look at the lifecycle of a standard Nginx web server deployment. This process moves through the client, the daemon, and the registry in a specific sequence. The real-world workflow. Deploying Nginx. Imagine you want to host a simple website. Here is exactly what happens under the hood of the Docker architecture. 1. The command, the client. You open your terminal and type docker run -d-p is to at nginx. The client translates this command into a REST API call. It sends the request to the Docker daemon, the host. 2. The search and pull, the registry. The daemon receives the request and checks its local cache. If the Nginx image is missing, the daemon reaches out to Docker Hub. It downloads the image layers one by one. 3. The resource allocation, the daemon. Once the image is downloaded, the daemon doesn't just run it like a normal app. It sets up the isolation environment. Namespaces. It creates a private network and process tree, so the Nginx container thinks it's the only thing running on the machine. C groups. It ensures Nginx doesn't steal all your RAM if the website gets hit with heavy traffic. Union FS. It adds a thin on top of the read-only Nginx image. 4. Port mapping, the bridge. In the command above, nansp 8080 is to 80 tells the Docker host to take traffic hitting your computer's port 8080 and funnel it into the container's port 80. Why this architecture wins? Of this decoupled structure, you get 3 massive benefits. 1. Consistency. The image you pull from the registry is bit for bit identical to the one the developer created. 2. Efficiency. If you run 10 Nginx containers, Docker only stores the base Nginx image once. Each container only takes up the disk space of its unique writable layer. 3. Portability. You can move the Docker run command from a Windows laptop to a Linux server, and because the daemon handles the OS level translation, it works the same. Summary table, component interaction. Action. Who initiates? Who executes? Resource use. Docker build. Client. Daemon. Local files plus base image. Docker pull. Client. Registry. Docker run. Client. Daemon. Image plus kernel. Namespaces /c groups. Like to try writing a simple Dockerfile yourself to see how we build an image from scratch, or should we look at how to manage multiple containers with Docker Compose?
Both.
That is the spirit. Let's bridge the gap between building a single custom unit the Dockerfile, and orchestrate containers, Docker Compose. Part 1. The build, the Dockerfile. Imagine you have a simple Python Hello World app. To turn image, you create a file named Dockerfile, no extension in your project folder. 2. Set the working directory inside the container, WORKDIR app. 3. Copy your local code into the container, copy/app. 4. Install any dependencies, run pip install flask. 5. Tell the container which port to expose, expose. 6. The command to run your app, cmd python link to app.py. The build command. To turn this script into a physical image on your machine, you run docker build my python app. Part 2. The orchestra, Docker Compose. Now, what if your Python app needs a Redis database to store data? You could start them separately, but that's tedious. Instead, we use Docker Compose link to .yml. This file defines how your web service and your database service talk to each other. The orchestration command. To start the entire stack, you just run Docker Compose up. How they feature Dockerfile, Docker Compose. Purpose: to build a single image, to run multiple containers. Output: an image, the blueprint. A running environment, the neighborhood. Focus: how do I install my app? How does my app talk to the database? The golden rule of Docker networking. When you use Docker Compose, it automatically creates a private network for your services. In the example above, your Python code doesn't need to know an IP address to find the database. It can simply connect to link to Redis. Docker's internal DNS handles the rest. Would you like to see a breakdown of the most common Docker commands you'll use daily to manage these images and containers? To master Docker, you don't need to memorize hundreds of commands, just about a dozen that you'll use 90% of the time. Think of these as your daily driver toolkit. 1. The essential daily driver commands. These are the commands that handle the basic life cycle of your applications. Command: what it actually does. Docker build, nit less than, name greater than. Build Dockerfile in the current directory. Docker run -d, -p, at is to at less than name, greater than, starts a container -d and maps ports and -p. Docker ps lists all currently running containers. Add a to c stop. Docker stop less than id/name greater than gracefully shuts down a running container. Docker rm less than id greater than deletes a stopped container. Docker rmi less than image_id greater than deletes an image from your machine to save space. 2. The what's going on. Troubleshooting. When things go wrong, and they will, these 3 commands are your best friend. Docker logs, f less than name greater than, shows the live output of your app. It's like looking at the console of a running program. Docker exec, it greater than bash. This is teleporting inside the container. It opens a terminal window inside the running environment so you can poke around. Docker inspect less greater than gives you a massive JSON file containing every tiny detail about the container, IP address, volume mounts, etc. The janitor, cleanup. Docker can eat up your hard drive quickly if you aren't careful. Every time you build an image or stop a container, bits of data. Docker system prune. This is the nuclear option. It deletes all stopped containers, unused networks, and dangling images in one go. Docker Compose, the multi-container manager. Since we talked about Compose earlier, here are the 3 commands you need for it. Docker Compose up nit entire stack, database, app, etc. in the background. Docker Compose down stops everything and removes the internal network it created, leaving your Docker Compose ps shows the status of all services defined in your link to .yml file. Pro tip: the container versus image mental model. If you ever get confused about which command to use, remember this math. If you want to fix the code, you must rebuild the image. If you just want to restart the app, you just handle the container. Would you like me to create a cheat sheet PDF summary for you? Or perhaps explain how to handle volumes so your data doesn't disappear when you run these commands?
cheat sheet.
Since you said yes please to both, I've put together a Docker strategy guide that covers the janitor commands and the mystery of volumes. Think of volumes as the external hard drive for your containers. Without them, if you delete a database container, your data is gone forever. With them, the data stays safe on your host machine. 1. The persistence layer, volume. In Docker, there are two main ways to keep data alive. A. Docker volumes, the internal pro way. Docker creates a folder on your computer that only Docker manages. It's faster and safer for databases. Command: Docker volume create my underscore data. In a run command, Docker run -v, my underscore data, skeptical smiley face, var/lib/mysql. B bind mounts, the developer way. You point a specific folder on your desktop, /logs, to a folder inside the container. Great for seeing logs or code changes in real time. In a run command, Docker run -v$ pwd code, skeptical smiley face app code my image. 2. Your Docker cheat sheet summary. Here is the condensed version of everything we've discussed. You can copy paste this into a notes app or save it as a reference. Actually, let me try that one more time. Since you said yes please to both, I've put together a Docker strategy guide that covers the janitor commands and the mystery of volumes. Think of volumes as the external hard drive for your containers. Without them, if you delete a database container, your data is gone forever. With them, the data stays safe on your host machine. 1. The persistence layer, volumes. In Docker, there are two main ways to keep data alive. A. Docker volumes, the internal pro way. Docker creates a folder on your computer that only Docker manages. It's for databases. Command: Docker volume create my underscore data. In a run command, Docker run -v my underscore data skeptical smiley face var/libs/mysql. B bind mounts, the developer way. You point a specific folder on your desktop, like .logs, to a folder inside the container. Great for seeing logs or code changes in real time. In a run command, Docker run -v$ pwd code skeptical smiley face app code my image. 2. Your Docker cheat sheet summary. Here is the condensed version of everything we've discussed. You can copy paste this into a notes app or save it as a reference. Lifecycle commands. Category, command, description, images. Docker build, -t app-v1, create an image from a Dockerfile. Images, Docker images, list all images on your machine. Containers, Docker run, -d-name, my app vsv1, run a container in the background. Containers, Docker PSA, see all containers, even crashed ones. Cleanup, Docker system prune, .af, delete all unused images/containers. The help me commands. Actually, let's try that again. Since you said yes please to both, I've put together a Docker strategy guide that covers the janitor commands and the mystery of volumes. Think of volumes as the external hard drive. To understand where Docker came from, you have to realize that it didn't actually invent containers. What it did was take a very complex, expert-only Linux technology and put a beautiful user-friendly handle on it. wanted to isolate an application, you had to be a Linux kernel wizard. Here is the timeline of how we got here. 1. The pre-Docker era. On my machine days. Before 2013, developers struggled with dependency hell. If you wrote code on Ubuntu and tried to run it on Red Hat, it would often crash because a tiny library version was different. 2000s. Technologies like FreeBSD jails and Solaris zones existed, but they were niche. 2000 Linux containers was released. It combined two Linux kernel features. 1. C groups, to limit resources, CPU RAM. 2. Namespaces, to hide processes from each other. The problem, LXC was hard to use, hard to move between computers, and had no image system. The Big Bang, .cloud. Docker started as an internal project at a French company called .cloud, a platform as a service provider. March 2013. The founder Solomon Hykes introduced Docker as an open source project during a lightning talk at PyCon. The innovation Docker didn't just provide isolation, it introduced the Docker image. This allowed you to package the entire environment into a single file that could run anywhere. The reaction, the room was stunned. Within months, it became one of the fastest growing open source projects in history. 3. 2014 to 2016, the standardization. As Docker exploded, the industry realized they needed a standard so that different companies didn't create competing versions of containers. 2014, Docker 1.0 was released, signaling this. 2015, the Open Container Initiative (OCI) was formed. This ensured that a container would work the same way whether it was run on Hat. 2016, Docker integrated Swarm, their orchestration tool, directly into the engine, sparking the orchestration wars against a newcomer called Kubernetes. 4. 2017 present, the Moby split and modern era. As Docker became the industry standard, it grew almost. To stay manageable, they split the project. Moby project, the open source Lego set for building container systems. Docker CEEE, the community and enterprise versions we use today. The shift. While Docker lost the orchestration war to Kubernetes, which is now the standard for managing thousands of containers, Docker remains the #1 tool for developers to build and run individual containers on their laptops. Why did Docker win? It wasn't because the tech was new, it was Docker made containers as easy to use as Git. You push, you pull, and you commit. It turned infrastructure into code. Key milestones table. Year. Milestone. Significance. 2013. Docker launch. Open sourced at PyCon. 2014. Kubernetes release. Google enters the scene to manage Docker containers at scale. 2017. Docker Desktop made Docker incredibly easy to use on Windows and Mac. 2019. Mirantis acquisition. Docker focus rather than enterprise servers. Would you like to know more about the orchestration wars, Docker Swarm versus Kubernetes, or perhaps how the Docker layers technology, Union FS, actually works under the hood? In the world of container orchestration, the battle between Docker Swarm and Kubernetes came a choice between simplicity and scalability. Both tools are designed to manage a cluster of machines, nodes, running multiple containers, ensuring they stay healthy together. However, they go about it very differently. 1. At a glance, key differences. Feature. Docker Swarm. Kubernetes. When we talk about managing multiple containers across When we talk about Docker Swarm versus coordinates, often referring to orchestration and cluster coordination,
What is this?
in 2026, the discussion around Docker Swarm has shifted. It is no longer a competitor to Kubernetes in the enterprise space. Instead, it has found its niche as the go-to tool for proportional complexity. Kubernetes is the operating system of the cloud. Docker Swarm is the easy button for small to medium clusters. Here is how they stack up in the current. In the demonstration, Docker Swarm and Kubernetes K8s are the two primary ways to manage a fleet of containers. While they solve the same problem, ensuring your app stays running across multiple servers, they have very different philosophies. Think of it like this. Docker Swarm is a reliable family sedan, easy to drive, gets you there. While Kubernetes is a commercial airliner, complex, requires a flight crew, but can carry thousands across the globe. 1. At a glance, key differences. Docker Swarm, Kubernetes K8s. Setup and complexity, very low. Built into Docker. High, requires separate installation. Learning curve, flat. If you know Docker, you know Swarm. Steep, many new concepts. Services. Scalability, good for small to medium clusters. Massive, can handle thousands of nodes. Auto-scaling. Manual, requires third-party tools. Native and highly advanced. HPA, VPA. Networking, simple overlays, out of the box and customizable. Service meshes, ingress. Ecosystem, smaller, focuses on the Docker way. Massive, industry standard with endless plugins. 2. Docker Swarm, the simple choice. Docker Swarm is native orchestration. If you have Docker installed, you already have Swarm. You just type Docker Swarm in it, and you're a cluster manager. How it works? It uses the same YAML format as Docker Compose. You define a service, e.g., 5 copies of Nginx, and Swarm distributes them across your available servers. Best for small teams, startups, or edge computing, where you want minimal, don't have a dedicated DevOps team. 3. Kubernetes, the industry giant. Kubernetes was open sourced by Google based on their internal system, Borg. It is designed to be unbreakable and infinitely flexible. How it works? It introduces a new unit called a pod, the smallest deployable unit, which can hold one or more containers. It uses a control plane to constantly monitor the actual state of your app versus the desired state. Self-healing. If a server dies in the middle of the night, Kubernetes doesn't just restart the container. It reprovisions the entire network path and storage to a healthy server automatically. Best for large enterprises, and apps with highly fluctuating traffic, like an e-commerce site during Black Friday. 4. The 2026 perspective. Which should you use? The orchestration war is largely over, and Kubernetes won the market share. Most cloud providers, AWS, Google, Azure, offer managed Kubernetes, EKS, GKE, AKS, which handles the hardest part, the setup for you. However, a trend in 2026 is the complexity tax. Many small teams are realizing they spend more time managing Kubernetes than writing code. The rule of thumb. Use Docker Swarm if you have less than 100 containers and want to deploy in minutes. Use Kubernetes if you need enterprise security, RBAC, complex networking, or if you plan to scale to a global level. Summary equation. Would you like me to show you a side-by-side comparison of a Swarm file versus a Kubernetes manifest for the same application? That is a great question. Because Docker sits right in the middle of writing code and running servers, it appeals to a few specific groups of people. If you fit into any of the categories below, you'll likely find these concepts clicking into place fairly quickly. 1. The "it works on my machine" developer. If you have ever sent code to a teammate only for them to say, "it doesn't work for me," you will understand Docker instantly. Why? You'll view Docker as a safe game for your environment. You're not just sending code, you're sending the whole computer it runs on. 2. System administrators and platform engineers. If you are used to managing virtual machines, VMware, VirtualBox, or physical servers, superpower. Why? You already understand IP addresses, ports, and file systems. Docker just makes these things disposable and fast. You'll appreciate not having to manually install Java or Python 50 times. 3. Visual learners, the Lego thinker. If you like building things with blocks or following IKEA instructions, Docker's architecture makes perfect sense. The image equals the instruction manual. The container equals the assembled furniture. Docker Compose equals the room. 4. Automation and QA testers. If your job involves running the same tests over and over in a clean environment, Docker is your best friend. Why? You can start a fresh database, run a test, and delete the whole thing in 3 seconds. No leftover data from the last test to mess things up. Is it hard for everyone else? Honestly, the hardest part for beginners isn't Docker itself, it's the Linux command line. Because Docker is a text-heavy tool, you spend a lot of time in a black terminal window. People who are used to clicking buttons in a GUI, graphical user interface, often find the first week frustrating. Once you get comfortable with the terminal, the rest is just logic. The aha moment. Most people have their aha moment when they realize, I don't need to install a database on my actual laptop anymore. I can just borrow one in a container and throw it away when I'm done. Since we've covered the who and the how, would you like to see a list of the sources, videos, sandboxes, or documentation to actually start practicing these commands? To use Docker in 2026, the requirements depend on whether you are using Docker Desktop, the user-friendly app for Windows, Mac, Linux, or Docker Engine, the lightweight version typically used on servers. Here is the current breakdown of what you need to get up and running. 1. Hardware requirements. Regardless of your OS, your hardware needs to meet these minimums. Processor, 64-bit processor with SLAT, translation support. RAM, 4 GB minimum, 8 GB is strongly recommended if you plan to run multiple containers or use Kubernetes. Virtualization, you must enable hardware virtualization in your computer's BIOS UEFI settings, usually labeled as Intel VTX or AMD. Disks is 25 to 40 GB of free space, images and logs can fill this up fast. 2. Operating system requirements. Windows 10 11s, Home, Pro, Enterprise or Education. Subsystem, WSL2, Windows Subsystem for Linux, is the modern standard. You'll need to ensure the WSL feature is turned on. Alternative, you can use the Hyper-V backend on Pro Enterprise versions, but WSL2 is significantly faster. Mac OS chipset supports both Apple Silicon M1, M2, M3, M4 and Intel chips. Version. Docker generally supports the current version OS plus the previous 2 releases, e.g., if we are on Mac OS 16, it supports 14, 15, and 16. Rosetta 2. If you have an Apple Silicon Mac, some older images might require Rosetta 2 to be installed via the terminal. Linux, Kernel, version 3.10 or higher. Officially supported on Ubuntu, Debian, Fedora, and RHEL. Desktop. For Docker Desktop on Linux, you need a desktop environment, GNOME, KDE, or MATE, and KVM virtualization support enabled. 3. Software and environment requirements. A terminal. You should be comfortable using PowerShell, Windows, Terminal, Mac, or Bash, Linux. Internet connection. Required for the initial download and for pulling images from Docker Hub. Docker Hub account, optional. You don't need an account to run containers, but you do need one if you want to save push your own images to the cloud. 4. Licensing, the business requirement. It's important to note that while Docker is open source, Docker Desktop has specific rules. For personal use, small businesses under 250 employees and less than $10 million in revenue, and education open source projects. Paid. Larger companies require a paid subscription, Docker Pro, Team, or Business. Pro tip for 2026. If your computer is a bit older or you don't want to install anything, you can use Docker sandboxes or play with Docker in your web browser. These allow you to practice all the commands we discussed without meeting any of the hardware requirements above. Would you like me to guide you through checking if your specific computer is ready for installation? It has been a pleasure walking you through the world of Docker, from the tiny layers of a Dockerfile to the massive orchestration of Kubernetes. We've covered how Docker revolutionized the way we build, ship, and run software by solving the age-old, it works on my machine problem. Whether you're a developer, a sysadmin, or just a curious learner, you now have the foundational roadmap to start containerizing your own projects. Join the journey. If you found this breakdown helpful and want to stay ahead of the curve in DevOps, cloud computing, and AI-driven development, subscribe to stay updated on new deep dives. Hit the notification bell so you never miss a tutorial. Share your thoughts in the comments. What Docker concept are you going to try out first? Thank you for exploring Docker with me. Happy containerizing, and I'll see you in the next one.
Thank you everyone. See you.